going to start off. Thank you for being here. My name is Gustavo Chavez. I'm a PhD student in applied mathematics. I work in the Geometric Modeling and Scientific Visualization Center. And it is my great pleasure today to introduce our keynote speaker. He's Bill Baxter. He works in Google Seattle in the Google Maps team. Before that, he was in Microsoft doing also graphics. And before that, he was in Tokyo. He graduated from one of the top schools in graphics back in the States, and his passion is about graphics. The content of today's keynote is about, listen to it well, the Steve Jobs last laugh. And why is that? He's going to talk about a disruptive technology called WebGL. And this has to do with, I'm sorry for the technicalities, but with the graphic processor cards that nowadays we're really fortunate to have, and how this technology is going to completely change the way the websites and the mobile technology works. So please help me to introduce Bill. Let's give him a big applause.
All right, Gustavo, thank you very much for the introduction. So I'm going to talk about WebGL and Google Maps. And the first thing I'd like to point out is I'm here. I'm glad I made it. It was a long trip. But I have to say I'm not totally sure why I'm here. I mean, I took a look at the keynote roster, and we've got a great talk yesterday about the origins of the universe and what everything means, and a talk by a guy who's saving the planet one ecosystem at a time, and Jane Goodall was supposed to be here, and CEOs are going to be talking, and a guy from Google. Well, I hope I can stand up to the in the same general vicinity as those other luminaries that are here. I'm very honored to be invited to talk in the same lineup with those people. So my goal here is I'm aiming high. I'm hoping not to bore anyone to death, and if I do, I'll be very sorry going home because it's a terrible thing to have on your conscience. Okay, so today's talk will be a sort of mingling of these three threads, these three themes, maps, web applications, and 3D graphics. And so the first thing I'll get right into is this product we launched recently called MapsGL. And it's a good way to start because it combines all three of those, the notion of maps, 3D graphics, and it's a web application. So to put it all in perspective, I'm going to go back a little bit, back to 1991, and do a little history here. In 1991, Silicon Graphics, they had created this fantastic piece of hardware that could do real-time graphics rendering like nothing before. And they needed a language to run it, a way for developers to access that power of their hardware. And so around 1991, they developed something that at least became what we know today as OpenGL. And one of the key players of that, in that effort, was a guy named Alan Rockwood, which you might recognize because he's your esteemed web chair. So that's a sort of interesting connection between all the things I'll be talking about tonight with WebGL and Kaust. So a little bit later, in 1996, some people there at SGI thought of something really interesting they could do with their infinite reality machine. And they came up with this demo that they called From Space to In Your Face. And one of the people working on this was a guy named Brian McClendon. And the idea was basically to use their super hardware. They realized, we now have the power to do a real-time graphics zoom all the way from space, looking at the planet, and zooming all the way in to human scale and below in one seamless zoom. And nobody had really seen this kind of thing before. This is back in 1996. And thanks to Brian's I guess, closet diving that he did. He found this VHS tape back in one of his closets and copied it up to YouTube. So we can take a look at it here. It's a very classic look to it, you can tell. This is zooming in on the Matterhorn here. Well, this is actually really, it's pretty amazing for 1996 real-time graphics. Google Earth today doesn't look a whole lot different from this. The main thing that's changed is that it doesn't require hundreds of thousands of dollars of hardware in order to see Google Earth now. We can do it on pretty much any home PC. It even runs there's a Google Earth client for phones as well. And also I'm told that this was a little bit hacked up. There's some trickery here. It's unlike Google Earth in that in this demo, you can only go see the Matterhorn. You can't go anywhere else. If you go anywhere else, there's no data. And apparently that was because they needed to get all of the data to fit on the graphics memory to do it fast enough for this demo back then. So this was done on the Infinite Reality machine with the Iris Performer scene graph library. It goes on for a little bit longer, but I'm going to go ahead. So later on, some of these guys from SGI left to start a startup called Intrinsic that was working on a scene graph that would be sort of the scene graph to end all scene graphs. And that lasted for a little while, and I think that there must have been something about this idea of creating an Earth viewer that really caught Brian and some of the other guys, caught them up in their spirit, that they really wanted to see this happen. And so they broke off from Intrinsic as a spin-off to create this company called Keyhole. And in 2001, Keyhole created something called the Earth viewer that was based on OpenGL. And at this time, it could work on fairly normal machines. They caught the attention of two guys at Google, some of the senior executives, and in 2004, Google bought Keyhole, and by 2005, that team, including Brian McClendon, who is now VP of Engineering at Google, they caught his attention, and they released Google Earth, the first version of it in 2005. In 2005 also, Google released the first version of our Google Maps. And this was actually, the 3D stuff was nice, but this was a web application that really blew people away, because I don't know if you were using the internet in 2005, probably most of you were, but you'll remember Maps before that had this property that you would look at a viewport, you'd click on a button, you'd wait for it to refresh, you'd click again, and it was deathly boring and difficult to use. And suddenly, with this new technique for the web called AJAX, it's asynchronous JavaScript with I forget what it's called, what the acronym is all for, but basically it's the asynchronous HTTP request that you can make in the browser to do some fetching work over the internet in the background while your user thread stays active. So this allowed the Google Maps to be like you see it today, where things are smoothly panning all the time, very interactive, and the data just sort of loads in the background as the internet fills in the queues. In 2007, another big exciting leap for Maps was the launch of Street View, where you could go in and see street-level imagery of lots of places around the world. In 2010, the Google Maps mobile client for Android debuted this OpenGL rendering of 3D buildings. So if you go into cities, you'll see these buildings pop up, and you can spin around the city and see it in beautiful 3D glory. And so just last year, in 2011, we launched the Google MapsGL product using WebGL to bring that same sort of interactivity to the web client, to the browser. So I'd like to go into my MapsGL demo now. And this is the dangerous part, because I'm actually going to do it live. I'd like to give a big shout out to Ali and the IT team, who spent most of the afternoon here trying to figure out how to get me fast internet up here. Otherwise, we would have been staring at hourglass cursors for an hour and a half. Okay, so I'm going to just briefly go back to the original, to the classic. I have the MapsGL turned on now. And if you go to Google Maps today, this is what you'll see. Something like this pops up saying Experience MapsGL. And if you'd like to give it a try, you click the button. We'll do a quick check of your browser to see if it's able to run WebGL and if it's able to render our maps fast enough. And if everything checks out okay, then you're in WebGL. And it's somewhat anticlimactic at first because you'll see it looks pretty much just like the regular maps. But the subtle differences start to show up pretty soon. If we zoom in here on different places, let's see. This is my home area. Here's Seattle. If we start to zoom in here, you'll notice, unlike image tiles, the text stays clear as you zoom in. And we get into the building level, we start to see some of these 3D buildings. Let me close that up so we got a full screen. Yeah. You see these buildings as you pan around. It's nice and smooth. So it's very exciting. It's the kind of dynamic rendering that just wasn't possible when we were taking static image tiles from a server. And we can do exciting things here too, like if we drop in the Street View guy, you can see here all the Street View zones. If we drop it in there, we do a dynamic zoom down to the level with 3D rendering right into the panorama. And another thing to notice there is that this is still in the WebGL rendering code here. We don't have to go to a plugin. We used to have to switch over to a different plugin architect, a different plugin in order to do the rendering for Street View because we couldn't do it with the native browser technologies. And that led to kind of we couldn't do a 3D transition into it, for instance, because you have to have this big switch over to from one window to another. Okay, so when we're done with the Street View, we can go back out. And I'll go to an interesting place that has some nice data. So this is Rome. If we start to zoom in on Rome, you can see another feature of the 3D maps here, the WebGL maps. Just normal satellite view so far. But as we get closer, at some point, oh, did you see it? It's pretty fast. But as we zoom in to this closer zoom level, we get this oblique transition. And once we're in the obliques, we can zoom around, we can fly around. And also here we can also drop into Street View straight from there. We're in the Colosseum now. And this is pretty cool. You know, you don't have to go to Rome now. You've seen it. Check. And you can even walk around in here a little bit, go outside. When you're done, exit back out, and there you are, swooped back into the world. And one thing that's really fun here is to go way out and drop the peg man down. So you get a really big swoop that way. It's fun. It's very exciting. And so all this kind of dynamic, interactive, switching back and forth between different modes, those 3D meshes that we're rendering for the close-in levels and the panoramas that you get when you go into Street View, it's all one rendering engine built on top of WebGL. So let me go back to the talk now. Okay, so one thing I didn't mention, one thing that's nice about this is that instead of sending images, a bunch of little images down to the web browser, now what we do is we send just a vector representation. Where are the roads on this tile? Where are, the little, what's the text? Instead of having to send an image of the text, we send the actual, just the string that represents different points of interest, and we render those dynamically on the client. So that gives us like lots of new flexibility for how we render things and changing the look of things dynamically depending on what's going on, and we didn't have that flexibility before, so that's very exciting. Vectors also happen to be smaller, so the amount of bandwidth used for transferring back and forth is usually smaller using vector representations as opposed to the raster representation. We can do these animated 3D transitions, as I said, and no plugin required. So if you have your WebGL browser, when you go to Maps, it doesn't ask you to install something new. It doesn't say, oh, you know, you have to go to this other site and find this other program and install it. And that's very great. So it works best with modern recent versions of Chrome, Firefox, Safari. In Safari, you need to go and tick a little preference option right now. Some graphics cards are not so great at this moment, but we will support as many as we can, and for things that can't handle the new WebGL, we'll fall back to a classic rendering mode. So if you want to try it out, you can go to maps.google.com/GL and give it a look. You don't even really need the GL. You can just go to the regular Google Maps. So I'm going to talk some about web apps and WebGL now, in general, the technology behind MapsGL. So before I get into WebGL itself, I need to take a step back and talk about web apps and why do we even care? What's the point of doing apps on the web? So the allure is this. I mean, there's many things here, but there's no install. You click on a link and you're ready to use the application right away. There's no installation process at all. So it's very low friction for users. The apps are always up to date because anytime you click the link, you get the latest version of the code that comes down over the internet. Any computer can be your computer. I mean, you know this. I think the email system of the university is Gmail. So anywhere you go, as soon as you type in your name and password, that computer effectively becomes your computer, and that's great. You don't have to carry your computer around with you everywhere just to be able to access your data. And related to that is the ability to seamlessly migrate. You know, I check my email on my PC here, and then I got to go, so I pick right up where I left off on my phone, and that's allowed by this web app model. Another point is that Google probably has a better computer than you do in their data centers. That's not critical for a lot of kind of apps, but for compute-intensive apps, that can be a big winning factor. And particularly in enterprise scenarios where people are trying to do a lot of compute-intensive work, it's a very compelling argument for web apps. Data in the cloud can actually be safer than your hard drive unless you're very particular about your backing up. The chances are that Google's data replication policy is better than what you're doing at home. It was certainly better than mine when my hard drive failed a few weeks ago. And another thing is web apps tend to be more secure than other kinds of applications. They run in sort of a sandboxed environment, and they can't take over your machine very easily. And it's also a fairly nice development model for the developers making these web apps. Most ways you make web apps involve writing dynamic code like JavaScript, and it has a nice edit refresh property. You make one change, you don't have a big recompile cycle, you just make the change, refresh in your browser, you see the result instantly. And some of the new browsers like Chrome have really good tools built in for debugging your web applications and sort of analyzing them 9 ways to Sunday, all kinds of different ways. But it's not all roses and ponies and rainbows. There are some downsides to web apps. There's no ownership of your software typically. The company that you're getting it from may ask you to pay every month. It's never your code. It's sort of the flip side of of always having the latest. Also, another downside of always having the latest version of the code, maybe the bugs get fixed, but also maybe new features get pushed that you're not too interested in. You liked the old way. You don't have that option usually with web applications. Another big problem is when you don't have the internet, you don't have an application, and that can be an issue. But we're moving towards a world where internet is a utility like electricity, and you don't go anywhere today and expect not to have electricity. We're there in many places, and we will rapidly get to the world where internet is always available everywhere, I think. Data in the cloud can be kept from you. If the data is not on your hard drive, this bothers some people. It bothers people that have very highly sensitive data. They would like to have absolute control of that data. For other people, it's not as critical an issue, especially if you have a cloud service provider that you can trust. Also, web apps are somewhat restricted in functionality. And this is, they can't read and write files, for instance. There's just some restrictions that web apps have. Native apps can do anything they want on the machine. Most of these things that I've talked about are sort of intrinsic differences between web apps and regular applications. You can't change the fact that web apps reside on, Gmail is on the server at Google. But the last one is different, I think, from the others. The web apps are restricted in functionality is something we can actually do something about. It sort of came about that web apps are restricted in functionality because of the, Professor Hoyer was telling us about how they developed the web at CERN, and it was a way to just share static data for the most part. And what served their needs was something that would let you send text and images, and pretty much that's it. That's what they needed to share. They weren't thinking about, at least I don't think they were thinking about sharing, pieces of code and active components with each other at that time. But that's kind of what we've gotten to now. We've realized that you can do lots of things that way. But we're stuck in a platform that has some restrictions. But those restrictions don't really need to be there. And that's what HTML5 is all about. If you've heard people buzzing about that. It's not really a single standard. It's a collection of different standards that add new APIs to the web browsers that give it access to more resources, basically, more computer resources. One thing is a file API. It won't let you access any file on the computer, but it lets a web app save files to the local hard drive in sort of a segregated area. And that way it can have sort of persistent data that it can come back to later. There's audio APIs. The original audio APIs for the web basically let you start a sound when the web page loaded. It's not very good for say, trying to make a game if you just have the sound playing all the time. You need sounds to trigger in response to particular events and things like that. Anyway, there's a bunch of different APIs as part of HTML5. Another one is socket, web sockets that let web applications do direct socket connections instead of having to always go through HTTP. Another one is Canvas. That's the big one that's most relevant to what I'm talking about here. The HTML Canvas element is a way to do 2D drawing. It's kind of like a way to give web apps access to an API like GDI or QuickDraw on the Macintosh. A low-level drawing API that just lets you draw lines and circles and Bezier splines and things like that. But it's important to this talk because WebGL is built on top of the HTML canvas. So WebGL is not a part of the HTML5 collection per se. It builds on top of it. It's, some people consider it to be part of HTML5 because they all sort of came out at the same time. But it's a way to render 3D graphics in your browser using hardware acceleration. It is basically a version of OpenGL for the web with a JavaScript API for accessing the OpenGL API. And it gives you, through that OpenGL layer, gives you direct access to the power of the GPU hardware, the graphics processing units in modern computers. And it's not a plugin. It's something that's, it's a native API in JavaScript, and that has certain advantages. You can, from the same code base, you can manipulate the same DOM objects. As the elements in a web page are called DOM objects. And using the same JavaScript code, you can manipulate those and turn around and do some 3D rendering and mix them all together. So it's a standard put together by the Kronos group, which is the same group that does most of the OpenGL standards. And the WebGL group of that includes Apple and Google and Firefox, the Mozilla people, and Opera as well. And it's based on, the standard is based on the OpenGL ES 2.0 mobile standard. You may ask, this is for web browsers. Not all web browsers are restricted to the mobile profile. Why not use the full OpenGL? And that's because web standards are supposed to be something that can run anywhere a web browser can run. And we have web browsers on, on our portable phones, our portable devices. And so the idea was to use something that can be, allow you to write apps that are portable to everywhere using WebGL. So it builds on HTML5, namely the HTML canvas element that I was talking about. In order to do WebGL programming, you take the canvas element and ask for a particular kind of context, a 3D context to do drawing. And once you have the 3D context, that's where your OpenGL API is. It resides in that context. So current versions of Chrome, Opera, Firefox, and Safari, even Internet Explorer, if you use something called the Chrome frame, can allow you to use Chrome as the rendering engine inside certain pages of Internet Explorer. And there's somebody who's been putting together something called the IE WebGL plugin, which is a plugin that lets you support WebGL on Internet Explorer. So it's growing, it's becoming more widespread. But somebody might be getting bored now, so I think I should show some demos. Okay, you're going to love this. This is great. This is like WebGL in action. See that? That's rendered in the 3D hardware. That's a triangle and a square. It's great. Don't you love it? No? Okay, well, you guys are hard to please. Probably don't need my email showing. All right. Oh, maybe another demo then. How about this one? There we go. They're moving. And you can kind of tell it's 3D, right? Yeah, this is good in this way. All right, well, we can probably do better than that too. Let's see, what's this one? It's kind of a surprise for me too, because I put those numbers on there. I don't remember what was behind them. Oh yeah, this is a good one. So this shows that sort of the cool things you can do because it's not a plugin, because it's integrated right into the browser. So here we have just some normal HTML code behind here, some normal HTML text, and then sitting right on top of that is one of these canvases, and you can, because this is something you can do in web programming, you can make things layered on top of each other. Because this 3D canvas is on top, you just are able to composite it right in with the text. So that's the kind of seamless integration you can get. And I'll kind of jump into here and show you this, because this is in Chrome, you have this like document explorer kind of thing that you can get. This is like a developer tool. It's built into the browser. But we can see here the sort of structure of the document. Here you can see there's a div inside the body, and as I go through running my mouse over these P elements, these are just blobs of text. It highlights where that is on the screen. So we got, in this document, we have one div, and this other one, here's the canvas element. This is how you declare one of those HTML canvas elements in your HTML document. So it just says there's a canvas here, its width is 800, height 600, and that's where the 3D rendering is happening. Okay, so, and one more, which I think, oh yes, this is a nice one. So finally, enough teasing, I'm going to show you some real 3D graphics. So this is a nice automobile here, a very nice model of an automobile, the dynamic camera here. You can see as it starts up right away, and as the data comes in, it sort of incrementally builds the vehicle. What's great here is that this is not just a static rendering. This is actually live WebGL content, and they've got it hooked up to the keyboard. So if I hit the keyboard, I can start driving this car around. This is the best part about talking about WebGL, is I can like show these cool demos that I didn't have anything to do with making and get all the credit for it. So here I can drive around, the camera dynamically follows. You got shadows under the car. It's just really beautiful, nice reflections on it. And this is running, I'm pretty sure, at about 60 frames per second here. It's very smooth. That guy's going to keep greeting us as I switch back and forth. Okay, so I'd like to talk a little bit about why did we do this. It was actually quite a lot of effort to redo our maps using WebGL. And I think I've touched on some of the reasons why we did that. We think we can make better maps and more dynamic, and we'll have more flexibility, that sort of thing, using WebGL. But there's another reason, it's maybe less obvious, and that's to try to help make a better web overall. So WebGL is kind of, it's a new standard, and it's kind of like John Liu was talking about. It's an ecosystem. People often talk about software ecosystems, but it's when you start something new, you kind of start with a non-functional ecosystem, because the browsers don't really know what they have to do to support apps well, because there are no apps, and the app makers think, well, nobody's really supporting WebGL, so why should I make an app in it? It's too risky. And so the browsers say, well, nobody's still using WebGL, so why should we put a lot of effort into supporting it? So one reason behind our decision to go all the way with the MapsGL project is to kind of try to break that cycle. You've got a chicken and egg problem here, where the chicken is not really into it because there's not very many applications out there. So if we can kind of break that cycle by making one great application, it can help be a sort of motivator for web browser developers. And even if the web browser developers are very enthusiastic about WebGL, the way the software works, it's hard to really shake out all the kinks in a new platform without something, very serious, a serious application to sort of run it through all the paces. And so, when WebGL came out, we got lots of people writing really cool demos, but they're very targeted, and they're not really like applications. They just do one thing. They don't take a lot of input. They don't have a long life cycle. There's not a lot of interactions in there. So by building maps on top of WebGL, it's helped us work with the browser makers to help, including Chrome and Firefox and other browser makers, to kind of help push this platform forward. So we work on the maps, and it helps them refine the platform. And by having a better platform, hopefully it will attract more people to think, oh, WebGL, this is a pretty serious thing. We can rely on it. They're putting a lot of effort into it. And hopefully through that we'll get more applications and more widespread browser support, and the ecosystem will thrive. I should mention Chrome itself, actually, I don't know if this is very well known, but it's kind of got a similar goal. The goal of Chrome was also to help make a better web. It's Google's lifeblood is these web applications. And there was this quote by Steve Jobs, who said about why he integrates everything, why he has his company build everything from the bottom to the top. And that's, if your company is about user experience, you don't outsource part of that stack. You don't outsource part of the user experience. And for every web application, the part the user interacts with is the browser. And we may have great ideas for how to improve that browser experience, but if we're making the apps and we go to people and say, hey, great idea, why don't you do this? They may or may not be willing to take that up. But if we come to them with our own browser and say, hey, we implemented this, it works, check it out, isn't this great? Wouldn't you like to do this too? And in fact, it's open source, so if you want to adopt it in your browser, you can. And in that way, the idea of Chrome is to help push things forward. Give us a chance to kind of give the user the experience we want with our web apps. But we do it in a open standards kind of way. We work with other browser makers to come up with open standards that everyone's allowed to implement and that everyone agrees upon. So, okay, more demos. Talking too much. Okay, so this is sort of a fun, arty kind of demo here. What's going on here, it seems, is that there's a bunch of particles flying through space, little white particles, and when they intersect this 3D horse galloping model, they get big momentarily. They turn into big purple triangles. But it's just really kind of pretty. It's nice. Okay, if you've seen this thing called the internet, There's something. There's this thing called ManCat, which is became pretty insanely popular for a while. And somebody, I believe this is somebody from Google, decided to make a 3D version of it. Yeah. Please watch this. The song goes on like this for like an hour. It's infectiously happy. If you were asleep, I hope I woke you up. This one's really fun. This is like a mathematical visualization of something called hop-along fractals. This is like a really nice intersection of technology, math, and art, I think. There's just tons of little demos like this on the web that people have made with WebGL, and it's so nice because you can just go to it with a click. It's sort of the beauty of WebGL. This is, good. Just leave it on and listen to some music. Did I do this one already? Oh yeah, that's that one. Okay, last one of this batch. This is a little bit more serious. This is a data visualization. This is like groundwater around the world as a function of time. So we can kind of go through here. You can see the time on the lower right-hand corner. The month is changing. You can see how the groundwater levels change. This is kind of fun, and you can rotate it around. Presumably this is a useful visualization for someone, but I'm not totally sure. You can see the rainforest getting a lot of groundwater in the January period. But it's just a good example of the kind of serious work you can do with WebGL to deliver these kind of visualizations to people in a very seamless way. All right. So delving a little more into WebGL, the hardware accelerated drawing, the key idea there that they had back at SGI, and it's continued right down that same track since then, is to find parallelism in the drawing operations and exploit the heck out of it. You end up with something that's a little bit backwards sometimes, where you're, instead of saying, I want to draw this here, I want to draw this here, I want to draw that there, you're instead sort of looking at the whole scene and saying, okay, I'm here, what color should I be? I'm here, what color should I be? It's not really made for maximum convenience. It's designed to exploit the hardware, and unfortunately that means there's some things that aren't all that straightforward sometimes. But it's quite manageable once you get used to it, and you do get the performance. That's the big benefit. So I'm a software engineer, and when I hear a big talk with big ideas, there's something nagging at me saying, yes, but how does it really work? How does it work? Just show me some code, for goodness sakes. If you're not that kind of person, then I apologize for what's coming. But I am, and I would feel amiss if I didn't show you some of the examples of how, there's one example, it's 3 slides, and if you want to fall asleep during those 3, it's quite all right with me. So this first slide is just the HTML code you would write to sort of set up a page. It doesn't do that much. It has a title. It loads this one JavaScript file that serves as a library. It's got some utility functions in it to make writing the WebGL code a little bit simpler, so I can actually show it to you on one page. There's nothing really fancy in here. This script here is going to be our WebGL code eventually. It says when the window loads, we'll call this function called main. And this is where we'll put our WebGL code to start up to get the canvas context and draw. And then this is just the body where we have a heading that says some text, and this is the canvas element. And I put a border style of solid on it just so you can see it, because at this point there's nothing in it, so it won't do much. It has the title here, and it's got just this canvas with a black border around it. So let's put some stuff in it. So inside main, the first thing you got to do is get a handle in the JavaScript code to the canvas object, and you do that with this getElementID get element by ID. This is standard web API. This getGL WebGL context is part of that library that I loaded. This gets us from the canvas. It gets us the GL context, which we'll just call GL here for simplicity. And here's where the real magic of GPU accelerated rendering comes in. For everything you want to draw on the screen in WebGL, you have to write these shaders, vertex shaders and fragment shaders. Vertex shader is just some program that gets applied to every vertex that you're rendering. In this case, we're using the most trivial thing possible. We say the position that comes out of this function. You set the return value by just setting the value of this GL position. The value that comes out is just the position that you send in from the application, this position value. It's an attribute that gets provided for each vertex. So that's very straightforward. Fragment shader, fragment is a closely related concept to a pixel. It's slightly different, but you can think of it as a pixel for the purposes of this talk. It's in the fragment shader you say for each pixel what should the color of it be. So you're given, I'm not showing it here because we're not using it, but you're given the coordinates of the pixel on the screen, and you have to decide in the fragment shader what color should I make it. So in this case we're just going to make them all green for simplicity. So then you take the vertex shader and the fragment shader objects and you create a program. This is again a utility function in that library. You call useProgram to set it to be the active program. We're very close to done now. Then you have to somehow you have to get the data for the vertices. What's going to be the position of each vertex? You have to supply that to the graphics card, and that's done by creating buffers. All data in WebGL has to be put into buffers and sent to the graphics card. And the reason that's done is because the graphics card has separate and usually faster memory for accessing data. And so you upload that data to the graphics card once, and then you can render with it on the graphics card very quickly that way. So we create a buffer, we put some data in the buffer. This is 6 vertices, 6 2D vertices with, so that represents 2 triangles. And the other important thing about graphics hardware is that it only knows how to render triangles, nothing else really. And then you turn on that buffer, say I'm going to use this buffer now, and you give it a position location. This position location is what ties it back to that name that was in our vertex shader, this A position. And then you just say draw, say I'm going to draw some triangles using the current arrays that I've just bound with this bind buffer call. And then it renders. So let's see what we got. Yes, our first WebGL program, woohoo. It's very exciting. But now you know, that's all the magic there is to it. And we can come over here to our program. It looks like a quad, right? It looks like a square because we picked the vertices very carefully to line up to each other to look like it's a rectangle. But we can see that it's really 2 triangles by going in and changing one of the data values here. I'll refresh. There you go. So you can see I moved this vertex, and now you can see the 2 triangles. So for those of you who've done 3D graphics programming, that was probably a little rudimentary, but if you've never done any 3D graphics program, hopefully it was somewhat enlightening. Okay, demos. This time it's a little bit of a psych though, because this is actually a developer tool for writing shaders. But it's still very cool. Since it's all dynamic, these shaders get compiled on the fly in very little time. People have made these cool websites. This one's called Shader Toy. And you can just come in here and start to edit the code. I don't know if that's might be a little hard to see, but I'm just going to add to the return value here. I'm just going to say, just going to add a little value to it, 0.2 plus whatever they were saying before. And you can see I hit the button to recompile, and automatically we see the shader updated. You can play with different things. Here's like a time value here. It has time as an input to this program, to this fragment shader, so that it can do that animation. If I just turn up the factor on time, it should get faster. There, it's moving faster now. This is a really nice tool for debugging your shaders. You can put your shader, paste your shader into here, and try it out. And there's a couple of very nice, interesting shaders that people have written. This one is probably the craziest right here, this Android one. Where is it? I've lost him. Droid, that's why it's not Android, it's just Droid. So this is the graphics hardware rendering a quad, so just two triangles, just like what we did in our other program. It's rendering two triangles, but it's got an insanely complex fragment shader that for every pixel in these things does a ray tracing basically in the fragment. It says, okay, if the light, if you were viewing from this direction and your ray went this far, would it hit anything? No, it wouldn't. Okay, go a little further. Would it hit anything? Oh, yes, it would. It would hit the body of the android. Okay, so now we have to do a reflection and start tracing the other way. Does it hit anything? Oh, it bounces off his arm this time. And so this is how ray tracing works. It's kind of insane to do it in a fragment shader, but it's very cool that, you know, somebody did it just to show it could be done. That's the beauty of the internet. Another one, this is kind of related. This is another kind of version of the same thing called Sandbox. Here it compiles dynamically, so we can do things like, just pick some value, make this really big, well, really small. Whoa, see now. So it's really fun. I mean, this is the kind of, this is when I was talking about web development being kind of a nice environment. This is the kind of thing I'm talking about, the fact that it's so dynamic. You can write these little tools that run in the web that help you write your web programs, and people have made a lot of useful tools. There's another tool called the WebGL inspector, which will let you kind of examine the state of your entire program. Very highly recommended if you start getting into doing WebGL programming. Another exciting site, this is actually a startup, a real company that's basing their company around WebGL. It's called myrobotnation.com. I don't work for them, I just think they're kind of cool. So what you do is you go to their website and they have a custom sort of CAD CAM system that's tailored to making robots, and it's very easy to use. This actually was something, this robot here was made by my son. I gave him one of these robots for Christmas. So you make the robot on the site, and then you hit the Make It Real button, and in a few days, a 3D printout of your robot arrives in the mail. It's quite cool, and I wasn't, you know, I thought it was neat, so I got one for my son just to see, and he was ecstatic. He thought it was so much fun making the robot, and he loved putting all these crazy stickers all over it, and he loved when it came in real life. It's kind of magical. I think there's some real opportunities here in terms of you know, startups like this. There's new ideas to be had because of WebGL that weren't really possible before, were a little bit too cumbersome to make a business out of. Who knows what people will come up with WebGL, but it's, you know, it's early days for WebGL, and I think, you know, there's still a lot of opportunities that people just haven't thought of. You know, the clear one looking at this is, you know, what about 3D printing in general? You know, that's great, you can make robots, but what about a site that can help you do any kind of 3D printing? There's another company that's adopting WebGL in a pretty big way that I heard about at the last WebGL camp that was in San Francisco. A couple of people there from Autodesk, which is the company that makes basically all of the 3D modeling software in the world now. They own AutoCAD, and they own Maya, and basically all the major software packages that people use for doing 3D modeling. And they want to use WebGL as a way to enable online collaboration between different sites. So right now they have a problem that these model files are really heavyweight, and it's very hard to transfer them back and forth. You know, if you make a really big CAD model, it's not easy to show to your client. They have to have the software, they have to have all this set up, and then the model files themselves are huge. But they've started to develop tools that will let people upload their models to the web. They can point their client to the web, and their client can just look at the model, a sort of lightweight rendering of the model right there on the website. I think that's a really nice, innovative way to put WebGL to use. And if you actually have some artistic talent, you can make very nice looking robots. No offense to my son. So I can show lots more videos here, lots more demos. I'll just pick a few of these. I am not going to go through every single one. This one is perhaps pretty interesting. This is somebody who's written a volumetric renderer in WebGL. So this is great for looking at CAT scan type data. I know volumetric rendering is a pretty big research topic too, and methods to do it in real time as well as just new techniques for visualization using volumetric data are quite big. I saw a poster in the engineering building that was where the visualization team is, where they were doing something with volumetric data. So I think it's very interesting for research work in graphics to be able to show your results to people in this kind of interactive way. You know, the typical way we do things in graphics for sending out research papers is we make a video of it and then we send that off. But sometimes people will send a program, but there's always these incompatibility problems. I've been sent programs before for review and I open it up and it just doesn't work for some reason. But now you can put your algorithms on the web using WebGL and show your reviewers, like, see, it really works, even in a web page. Imagine that. Accepted. This guy does a lot of nice stuff. Evan Wallace has done some really nifty things. This is an interactive height field fluid simulation plus path tracing to get the water reflections. And you can drag in it interactively here and move this ball around. You can also change your viewpoint by dragging the square around, see it from underneath. It's really beautifully done. And from what I understand, basically all the computation is being done using WebGL. So it's GPU kind of water simulation where they use or abuse fragment shaders to do computation rather than rendering. Of course, Angry Birds is another sort of commercial thing that we can talk about. People using WebGL in actual applications. The folks that did Angry Birds, Rovio, have made a WebGL port of it that runs really nicely. I'm not actually going to start it up because the song will drive me mad. This is a path tracing demo. This is, path tracing is a really high-end rendering technique, very slow. Usually it's done offline. But this guy, the same Evan Wallace, put together this thing where it does it sort of incrementally. You can change the scene dynamically, and you see it's very fuzzy at first because it just shoots a few rays out into the scene. But as you let it sit, it refines until it's a very nice image. So that's very cool. It's another sort of example of how you could, even an offline rendering technique. Perhaps you could make a demo of it using WebGL that's live and interactive. This is probably something familiar to some people, but I think it's a really good educational example, perhaps even scientific visualization example. This was originally Google Body, and Google sold it to this company called Zygote. There we go. So you can see a body. I hope I haven't just made a major faux pas here. I can switch to the guy. Sorry about that. We'll have to wait again. They're not on the screen at the same time. Apparently the man is more heavyweight than the woman. Yeah. All right, well, that's interesting. The shaders were loading in a delayed way. All right, so we can take the slider here and go down and see the muscles and things. You can zoom in, and so you can imagine this. I mean, it's a great educational tool if you're a medical student trying to learn anatomy. Like, what was that thing called right over here? You can click on it. Oh, lung. That's right. Yeah. Medical school's hard. But anyway, you can certainly see potential for this. Also for doctors, if they had something like this in your office, the doctor could point to it and say, we're thinking of removing this. You have trouble with yours, I think. We need to see some more nice 3D rendering here. This is the level data from the popular Quake game put into WebGL. Somebody wrote a renderer for it. This guy, I forget his last name. Brandon is his name, though. All right, so you can see this is another one of those interesting things where it uses a texture, it uses like this checkerboard until it actually has the texture data loaded, but it lets you go ahead and start playing anyway. Looks like I died. I'm awesome. All right, so yeah, here you go. It's Quake. You've probably seen this before if you like games. It's been around a long time. This is kind of an old game, but here you go. You can see this is working quite well in WebGL. I'll do this as the last one here. This is a nice little city fly-through. It's like a procedurally generated city. It's another kind of hot topic in computer graphics. Seen a lot of papers on that recently. Procedurally generating cities. But you can fly around it here and interactively. We might see Anakin Skywalker flying around somewhere here. Okay, so I hope that's given you a nice feel for the sort of space of things you can do with WebGL. So going back to MapsGL, it's the combination of Google Maps with WebGL. I'm going to talk a little bit about some of the technical details behind it, just touch on it very lightly. So one thing about GPUs is that they're great at rendering textured polygons, and that's something that's wonderful for games. Games have lots of textured polygons. They're not so great at rendering lines, and they're not so great at rendering text, and they're not too great at anti-aliasing either. And those are all three things that we need for rendering nice maps. Maps have lots of lines and lots of text, and they look much better when they're anti-aliased nicely. So let me talk about some of the challenge in drawing lines. When I say lines, our road lines look like this. There's a very subtle outline around the edge of the roads, and they overlap in interesting ways. You know, if a road goes, if a road intersects with another road, then the outline should go on the outline of the combined intersection. If a road goes over another road, then one of the outlines should go on top of the other road. We also have these, they're fat and curvy, and WebGL simply doesn't have a fat, curvy line primitive. It has a triangle primitive. You render triangles. So the way we've ended up doing this, for efficiency's sake, is to do the road rendering in 4 separate passes. 2 passes for the straight rectangular segments of the road, and then for the joins that kind of connect the bends, we use a separate 2 passes. So to show you how that works, let me show you, this is the roads. It's very subtle, but I'll do a zoom in here. This is the rendering of just the straight parts with no joins, and you can see sort of a little afraid look around the edge of the loop where little gaps have popped in because those were part of the curvy parts of the road. And we fill those in using circle primitives. So there's actually no circle primitive in WebGL, but if you render 2 triangles in a square, you can ask in your fragment shader for every fragment in there, you can say, am I in the circle? 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 You basically pass down the circle equation that you want to render into the fragment shader, and so that way you can render circles. And it's fairly efficient too, because you don't have to send down a lot of geometry. And that's the thing with trying to render circles as triangles. You end up with a fan of triangles. You have lots of vertices in it. So with this technique, we rendered the joins first, and then we rendered the roads on top of them. And so they're lined up just perfectly. You can see the roads rendered with alpha here, with a little bit of transparency, and they are placed just so that they fill in those gaps with nice gentle curves. And for the more curvy the road, the more significant it is. So that's just a sort of interesting, and finally combining, you get the original roads I showed you. Anti-aliasing was another thing I brought out. This is, our tiles that were rendered on the server and sent to the client as images. We're using a software rasterizer. And using a software rasterizer, you can get very good anti-aliasing. If we zoom in on here, you can see sort of that nearly horizontal road towards the bottom there in the zoom. You can see there's nice, gentle gradations of color. That's what you want to see. When it looks like that zoomed in, it's going to look very crisp zoomed out. With no anti-aliasing at all, of course, it looks terrible. You can see jaggies everywhere, and the roads look kind of messy. Even if you can't tell that it's pixels or what it is, something doesn't seem quite smooth with them. And this was, I think, having really good anti-aliasing was one of our key advantages over some of our competitors from the early days. Some map providers weren't using anti-aliasing at all, and so people maybe didn't realize what it was about Google Maps, but things like that sort of quality makes an impression on people, and they thought it sort of affects the opinion of the overall appearance of the maps. So I think that's something we really don't want to lose in Google Maps. So most graphics hardware supports something called multi-sample anti-aliasing. It's part of the WebGL spec as an optional feature. So to say you have WebGL support, it's not required to support multi-sample anti-aliasing. And we are not really willing to get rid of anti-aliasing altogether, just if a client doesn't have it. We want to support it everywhere that WebGL is supported. So if you have multi-sample, we'll use that. You can see the quality of multi-sample isn't quite as good. There's some kind of artifacts in the edges. If you look again at the part going across the horizontal at the bottom, gently arced, I don't know if it really shows up on this thing, but you can see there's a little glitch near the top, and the number of gradations is fewer than with the software anti-aliasing. So for clients, you can actually get a slightly better result by doing 2x supersampling on the GPU. That means what we do is we render the entire viewport at twice the size, so 4 times as many pixels, and then put that entire thing into a texture. It's rendered into a texture, and then you use the texture as a texture map to render just a simple quad to the screen. And if you set your texture filtering properly, you can have the hardware do the combination of groups of 4 pixels together. You can have them do that linear combination of those 4 pixel groups together to get a fairly efficiently rendered 2x2 supersampling result. It's a lot of pixels to render things at 4 times their screen size when you've got a large viewport open on your desktop already. So it turns out to be too slow to do interactively. So for these, especially since the cards that don't support multi-sample anti-aliasing tend to be the ones that are not very high end. So what we typically do here is have the super sampling only when you stop panning the viewport. So when you're moving around, you get just standard aliased rendering with no super sampling or multi-sampling. And when you stop, it does this sweetening thing where it takes a moment, but it makes a nicer picture to look at in the end. But this is kind of just to compare with the two. You can see the 2x, 2x2 supersampling, software anti-aliasing. You can definitely see the difference if you're looking for details, and it's important to me. So, it's definitely an area where 3D graphics could use a little work. There's lots of recent research being done on something called morphological anti-aliasing techniques. And I've tried one. I tried one out called FXAA, and it didn't really work for the kind of data we have. It works well for 2 edges like this. You got one color here and one color here that come side by side. But in all of our roads, we have a little 1 pixel boundary that's the outline of the road, and it just does not work well at all in that situation. So I think that's an interesting area for further research, is trying to get better anti-aliasing techniques that you can implement in GPU hardware. But overall for us, so I've kind of pointed out some of the most annoying features of WebGL for us, but overall By far, the speed and flexibility that we get from being able to render pretty much anything we can imagine. Sometimes it requires jumping through a few hoops, but if you can imagine it, you can probably get it to render somehow at a reasonable rate. It sort of outweighs the headaches by quite a bit, we think. So that's sort of the first half of my talk, probably more than half. I'll go now into sort of pontificating about trends and the future of maps as I see it. And I should say that just because I say something here does not mean that it's like Google's next project or Google's about to release it. I'm just talking purely as somebody who's interested in this sort of subject, and things may or may not be being worked on by Google, but this talk is not about that. I'm actually going to talk about stuff other people are doing as well, so it's not just a Google thing here. So I'd like to show this. This is actually a talk done by our program manager, Bernard Seefeld. And he gave a nice talk at TEDx, and so I'd just like to, it's about 13 minutes long, something like that. I'd just like to show the whole thing, because he gives a really nice, he has an interesting perspective on the future of where maps are going, and he has some nice anecdotes. So I'd like to give you this little talk within a talk now, if that's all right. I'll start it up.
How many people would it take? Or some HR people are saying.
You gotta catch the first.
So if you were to map the entire world, how many people would it take? Or some HR people are saying, what kind of people would it take? So let's look at that. What kind of people would it take to map the world? So in order to figure this out, let's look at the people who mapped the world the first time, when we were at the cusp of creating the first complete map of the world. This is a map in the late 16th century, and you see a lot of familiar shapes, like Indonesia, India, all mapped. But you also see a couple weird things in the upper right corner. These are the areas that haven't been mapped yet, so they heard some rumors that they're big monsters and so on, so the cartographers said, here be dragons, pay attention, don't go there. Or be adventurous and go there. And there were other rumors. A lot of those maps were based on rumors. Like if you look at the lower corner, there's something called beach. That's based on the rumor that Marco Polo heard and brought back. And that's
well, I just got a good look at the time here, so I think I'm going to skip this in the interest of time and just summarize him brutally. He says a lot of interesting things in here, but the main point that he makes, he started off saying, how many people does it take to map the world? And what he goes on to talk about is how what's on a map depends so much on your perspective. The explorers who made maps early on would label things on their map like, cannibals here, don't go near. Last person that went there got cut into little pieces. And we don't put that on maps anymore. We don't usually put warnings. It's not what we're interested in anymore. And everybody who uses a map has some sort of different agenda, and what you put on the map kind of depends on that. So asking the question is, how many people does it take to create a map of the world, sort of misses the bigger picture, which is that it's like asking how many people does it take to write all the books in a library. It's like you can put anything there you want. There's an unlimited number of things you could put there, right on down to things that are very personal to a person. What events that happened in their lives. They may want that for their own record, to have personal events recorded here and there that they can just sort of keep and look at from time to time, or share with their loved ones. So, the answer is it takes everyone to have a complete map. You're not going to have a complete map unless you got everyone's perspective, basically. And that's because there isn't one single map. And I think, when you hear that question, you're thinking just the geography, just the locations. But if you look into what people do who study geography, they don't think about just the locations. It's not just the cartography. It's not just the locations of places. It's how everything people do relates to the place in which they did it. So all of that is sort of encompassed by maps, or it could be more so than it is today. So maps depend very much on the user and the usage they're being put to. So just going to list a few things that I see as big points of the future of maps, and one of those is personalization. Just as we were saying, it really depends on who you are and what's important to you what kind of data you have on your map. And very closely related to that, if you were to list the things that are important to people, very high on that list is going to be other people, their loved ones, their family, their friends, their community. It's something people are interested in, and so it sort of makes sense to have this socialization of maps as well. There's this, people that you're interested in or something you might want to see on your map, which is sort of reminiscent of this, this thing from the 1999 book by J.K. Rowling, the Prisoner of Azkaban, the Harry Potter book. In that book, she has this idea of a map that when you open it up, you can see your friends on it moving around. And I'm sure this seemed like quite a fantasy to her writing this book in 1999, that you could have something in your pocket that you pull out and you can see your friends. Sure, that would be cool if you had it, but of course we don't have that. But 10 years later, in 2009, we released at Google something called Google Latitude, and it lets you do pretty much exactly that. You can opt into the system and say, I want to share my location with my friends, or ask your friends, would you share your location with me? And if they say yes, you can actually see in real time where all your friends are on the map if their phone is on. It's basically fantasy turned into reality in a very short span of time. I mean, things are evolving rapidly in this world. Technology is changing quite a pace. 1999, smartphones weren't that smart. It was hard to imagine that in just 10 years we would have this kind of thing where we could actually see each other on our phones. So there's lots of companies that are looking into this space, not just where people are, but what people that you know think about different places and their opinions about it. Glimpse is a startup that lets you share your sort of current track as you're heading to a destination. You can give it to send a friend an email through Glimpse that says, I'll be there near 7:30. You can follow this link to see where I am exactly in real time as I get closer. And of course, all these other sites, Yelp and Facebook and Google Plus, are all very interested in tying place and sharing other information. So I think socialization is a big thing. But if we think about where that's sort of headed, why are we able to do this kind of sharing today? It's because everyone has something that is essentially, a portable sensor package that they're carrying around with them these days. These smartphones, they've got GPS, they've got cameras usually, they've got a persistent connection to the internet, and these things are everywhere. And they're growing like leaps and bounds here. So in 2008, smartphone shipments actually outstripped laptop shipments at about 175 million. 150 million is where they passed. In 2011, we had the point in the United States where smartphones outnumbered traditional phones. So more smartphones than traditional phones. And showing the rest of this graph, it's predicted that by 2013, the number of, late in 2012 even, the number of smartphones being shipped will outstrip the total number of PCs, laptops, and desktops. So the number of these things is just growing by leaps and bounds. Everybody has one. And if you think about it, it's like this, it's like a distributed sensor network, but a really high quality sensor network. When people talk about sensor meshes, they're usually talking about a tiny little temperature sensor that has maybe Wi-Fi or some other low power communications built in. But they have full internet connections, they've got cameras, they're megapixel, they've got GPS, and in addition, they've got smart operators, intelligent operators, that you can, if you can employ their services and get them interested in the problem that you're trying to solve, you can direct them to do some exciting things. So just how many of these do we think we have? We've got, a recent statistic I found is in 2010, about 68% of the world uses a mobile phone, and 17% of those are smartphones. Do some simple math, you get about 800 million smartphones out in the world, and that is a big sensor network. And that's actually being put to use in one way right now in terms of gathering traffic data. So you've got governments have sensors embedded in the roads they've had for a while, and you know, cameras and traffic. That only covers about 6,000 kilometers in the U.S., 6,000 miles, sorry. There's a company called Intrex that has some contracts with trucking companies and other fleet vehicles to upload GPS data about where the vehicles are. But also recently, Google in 2009 enabled a service where if you opt in and say you're willing to share your position, they'll use your GPS data, anonymized of course, in such a way that you can't tell who it is. It's just the middle part of your trip will be data points will be sent up. That goes to the cloud, and we can figure out from that a good estimate of how much traffic is where, if enough people are doing it. And from that data, we then beam it back down from the cloud to anybody who has who has one of these devices. So that's very exciting. And these also have cameras, of course. There's lots of interesting ways to make use of cameras. One thing people do with cameras is take pictures, and surprisingly they upload them to the web for everyone to use. So that leads me to this project. It's called Building Rome in a Day. All these little triangles here that you see are pictures that were retrieved on Flickr with a search for Rome or the Colosseum. You search by keyword, you turn up tons and tons of pictures people have taken of this thing because it's a tourist attraction. And these fellows at the University of Washington, Samir and Yasutaka and others, took all these camera pictures and used a massively parallel system for trying to reconcile all the different camera views, figure out, are these two views looking at the same thing? Reconcile the views using stereo vision techniques, and build this 3D model from it. So this is completely done from a set of randomly selected photographs. I should say the other thing is the photographs they selected were all geotagged, so you knew approximately where they were to start with to make the problem a little easier. So 3D modeling from basically, what happened there? Oh, Samir, hi. That's actually a link down there, okay. So aggregation of data from lots of sensors to do these traffic kind of things, or getting pictures from lots of people and aggregating it together to kind of create more detailed map information. So we get 3D in the case of the Rome in a Day idea. Street view is another kind of approach where we don't aggregate it from lots of people, but we actually go out and just brute force try to capture a lot of data. We do that by driving these cars around, and recently we've started adding trikes to get to places where cars can't go. For instance, they went to the Stonehenge and rode their trike around. I think also the Colosseum there, that data inside was done by one of these trikes. But if you think of where these stereo vision techniques are going, combined with what's possible in hardware accelerated rendering, this is a current game. This is all hand modeled and carefully constructed models of the environment. But this is kind of the level of detail that's possible now on graphics hardware. And if you think about it, we're able to go through a scene, and using stereo vision techniques in our brain, we're able to reconstruct some sort of model of an environment. Here they just went inside, transitioned to indoor. I think there's some very exciting possibilities in the future by pushing on this stereo stuff. And if you think I'm crazy that we could ever get there, this is a demo by the folks at Nokia. It's a beta example of. It may take a little while to load. So this is also using WebGL, incidentally. We zoom into New York here. The data takes a little while to load. Looks a little weird at first, but when the higher resolution data finally shows up, you'll see that this is a really amazing digital model of the city. And there's no way, I don't believe, that they could have done this all by hand. And some of the artifacts you see make it definitely look like it's a computer vision based technique. So if we can get this kind of detail for this level of city view, it should be possible. I think within 10 years we'll see something on the level of that of that game in terms of rendering. So, from Street View to, Quake View, you might want to call it. There's another demo here from a company called C3 that was recently acquired by Apple. They've got something very similar here, where they've taken probably low-level airplane flyovers and stereo computer vision and put together really realistic models. This is amazing. Like me and some of my colleagues were just flabbergasted by how awesome this looks. It looks almost like a tilt-shift camera effect, where you've got kind of a little world. Looks miniature for some reason. Okay, so vision and acquisition and automation of creation of maps is one big thing. So I know I'm running out of time, but today, I talked about these three themes: maps and web applications, and how they all tie together. I think there's lots of things we can still do. If you may have seen Street View and thought, wow, we've got kind of all the streets in the world mapped. What else could we do? There is tons more to do. There's so much more interesting stuff at high-end scale, lots of data, lots of processing, lots of math to do this kind of computer vision, and really more refinement is needed on the computer vision algorithms. We're not quite there yet. But those are the things I see as sort of the driving forces in maps going forward. I think there's very exciting times ahead for mapping and lots of things that can be done. And WebGL is one of the coolest enablers there. So some acknowledgments. I didn't do MapsGL by myself. I hardly, compared to these other people, had anything to do with it. The other people on the MapsGL team have done a phenomenal amount of work. I really thank the Geo leadership, and also KAUST. Thank you, Gustavo, for inviting me, and for the conference chairs, and Ari Laurie. So thank you. Okay, yeah, I apologize I haven't left much time for questions, but Alan says we have 5 minutes. 3 questions, did you say?
3 questions.
Hello. So my current question is, do current smartphones have the hardware capabilities to render WebGL pages? Or
Do smartphones have the capabilities?
The hardware acceleration capabilities?
Yeah, I think it depends on what you're trying to render, but they do have enough capability. I mean, if you've played games on your phone, then you've seen OpenGLS on those devices working. So that class of graphics capability is possible in a web page. And this is an interesting thing about the iPhone is it actually has WebGL support. It's just they've decided for now to limit it, to restrict it to the iAds. So if you're making iAds, you can use WebGL to create them. And I guess they feel that's safer for right now until they feel more comfortable with the WebGL technology. That way they can sort of, every time somebody uses it, they get to vet it. They get to analyze it and see if it'll, make sure there's nothing crazy going on or malicious in the application.
Okay, thank you.
Hey, sorry, I'm ready. I've just got a quick question. Sorry, I'll stand up. Yeah. Could not all the 3D applications be done in pay-per-view and Flash with ActionScript?
Say that again?
The 3D applications that you've been talking about.
Right, right.
They've been progressed before in pay-per-view, which is an open source application in Flash. Does this perform better, or is it just it's open source, much more accessible? And why is this much newer than pay-per-view, even though it's been around for
right.
a long time?
So you're talking about a particular engine that's written on top of Flash?
Yeah, in ActionScript, which is
in ActionScript
3 is kind of developed 3D.
Which is pretty similar to JavaScript. Yeah, the main argument against it is that it's a separate piece of software that people have to download, and it creates sort of a separate little box. You can only make these little box applications that have a transition. They're separate from the rest of the page. They don't interact well with the other DOM elements on the page. You see a lot of these demos, a lot of the WebGL demos, you'll have little elements and controls on the side, and the heads-up displays. Those are usually done using HTML, like straight up CSS, HTML type stuff. So,
So you're saying it's much easier to write because it's based on HTML and CSS rather than...
Yeah, I think the main argument is that it's better integrated into the web developer tools. If you're really writing something that's completely standalone, I don't think Flash is going to go away anytime soon for these really separate experience apps. There's also a plugin from somebody called Unity, which is pretty popular right now.
Yeah, the operator using Unity, isn't it?
I'm sorry?
Do you think this means that Flash is going to slowly die and disappear because it's an expensive application to use?
I think it kind of already, it already is. They've already made some announcements about backing away from mobile support. They're sort of pulling away from that. So I think, Flash is not going to last forever, and I don't think 3D is going to save it.
Thank you.
Last one.
Can you share with us the WebGL application shared in your presentation?
Can I share with you the list of demos?
Yeah, it's demos.
Certainly, yeah. I can give that to somebody who's able to distribute it to everyone. I guess I can put it on the Acaddocs page. I think I have a way to put notes on there, so I can put it up there.
Much better.
Yeah.
Thank you.
Okay, that was the last one.
So, thank you very much, Bill. This is from the whole CAUS community. We would like to thank you for the nice talk you gave today. Very inspirational. We love the work you've done in Google Maps. So this is for
Thank you very much. Appreciate it. Oh, that's nice.
Thank you for coming tonight. We'll see you tomorrow.